Hey everyone, and welcome back. It's been a while since our last video. We have been absolutely hammered busy, and of course, as I've said before, customers do come first. We've got many parts coming in off back order. We've got engines lined up that we're assembling. We've got bikes in the back that we are disassembling to start that process. So hopefully we can get more videos out here before too long, but again, customers do come first. Today's video is going to be an interesting topic, I think, one that I haven't seen anyone really touch on. It's not uncommon for folks after they've had an engine build for a while to maybe decide that they want a little bit more power. Invariably, they tend to look at the camshaft first, changing the cam, most often more lift in order to make more power. Now, the misconception, of course, is that more lift always makes more power, and that is not always the case. For the rest of you, you may have purchased a motorcycle that had an engine build done in the past, and you're not exactly sure what all was done, again, particularly to the cylinder heads. And unfortunately, I see folks that will just pick a camshaft based on the total lift alone, slide it in the bike. That can be a big, fatal mistake that I have seen on numerous occasions. Most of the time, if it's a big fatal mistake, when you hit that starter button for the first time, you know it. You'll hear a loud crash and a boom, and that is all she wrote. For others, I have torn down cylinder heads that have been done previously, and cams have been swapped, and seen clues that the individual that owned that motorcycle was very, very lucky, right at the edge of that catastrophic failure. You have to be very careful when you choose your camshaft and look at one specific number that seems to go unnoticed and undervalued. In today's video, I'm going to tell you where that number comes from, why you need to know it, and potentially help you save your engine. So stick around. In typical fare, you guys know how I am. I like to start with the basics. Not everyone that watches our videos has a vast knowledge of how engines work, the internal components, and what a lot of these terms mean. So we're going to start with the very basic principles of the four-stroke internal combustion engine to help everyone understand how critical this one particular issue is. So let's start with the basics. During the intake stroke, as the piston is coming down, your intake valve would be open in order to draw air and fuel into the cylinder. When you get to bottom dead center, both valves will be closed. Close enough, depends on your cam timing, of course, but for the most part, both valves will be closed after bottom dead center as the piston is traveling upwards during your compression stroke. Both intake and exhaust valves would be closed. Then you have ignition just before the piston reaches top dead center, and combustion propagation. It builds pressure in the cylinder, and that pressure forces the piston down during your power stroke. Again, both valves are closed during the power stroke. As the piston crosses over bottom dead center and starts coming back up, your exhaust valve opens in order to push the exhaust gases out. But another thing that happens as the piston is approaching top dead center, your intake valve opens as well. Yes, there is a point during the four-stroke process that your intake and your exhaust valve is open at the same time and off the seat. That is also the point that the piston is at top dead center. That's the point typically when both valves and the piston are at their closest point together during the engine's operation. That point is top dead center exhaust stroke, if you will. Now, that cam specification that I keep referring to that's so important is TDC lift, top dead center lift. That's referring to how far the valves are off the seat at this point in the combustion process. I picked 4 cams. I say relatively common cams. I started with the S&S 570 and then moved to the S&S 585. Then we went to the Redshift 577 and then an extreme change of camshaft to the Redshift 627. Now let's take a look at the TDC lift numbers. The intake for the S&S 570 is at 0.187, 187 thousandths. The exhaust valve would be off the seat 179. For the S&S 585, notice virtually no change. 186 for the intake, 179 for the exhaust. Now in this particular case, between the two S&S cams, that is quite a difference in total valve lift, but virtually no change in the TDC lift. So in other words, if a set of cylinder heads were set up to work well with a 570, they're probably going to work well with a 585 if we're just talking valve clearance while both valves are off the seat. Now let's move to the Redshift 577. I picked that one because it's, as far as total lift goes, it's pretty close to right in the middle of the S&S 570 and the 585. But look how vastly different your TDC lift number is. 214 thousandths on the intake, 197 thousandths on the exhaust. So what that means is if you are installing this cam in the same, all three of these cams in the same cylinder head, this cam is going to put the valves much closer together at TDC when they're both open than your two S&S cams would. Now let's do an extreme change in camshaft. I have seen folks go from cams in the 550 lift range to the 620 and 630 lift range without doing anything else, but I'll get to the other considerations in just a second. So let's look at the Redshift 627. Yes, quite an extreme change in total lift, quite an extreme change in TDC lift on the intake and the exhaust. You have 240 on the intake and 207 on the exhaust. Now, these are large differences in these two, and then also between those and each of those that we have to take into consideration. Now, there's several variables that we have to think about when we're machining the cylinder head and preparing it for a particular cam profile, the entire design of the engine. It kind of all works together, right? So some of those variables that would affect the TDC the valve-to-valve clearance at TDC, things like your valve size, your valve stem protrusion, the stem length, your rocker arm ratio. It's not uncommon for folks to take all of these numbers, typically your published cam numbers, your lift at valve numbers, your TDC lift numbers, all of those are based on stock rocker arm ratios. Now, if you grabbed a set of, say, 1.7 ratio rockers without changing the camshaft because the ratio is higher, your lift numbers are going to increase as well. So your TDC lift number would increase, your total valve lift number would increase as well. So we have to consider the rocker arm ratio in this if you are changing that. Now, all of these variables, these top three variables, are determined by how your cylinder head is machined. How far the valve is sunk into the head, how far the stem protrudes, the length of it, and that's very important part of cylinder head machining that I will touch on in a minute when we go to a cylinder head and compare the valve-to-valve clearances at these TDC lifts, so you get to see just how close they can get. Other considerations, doing a cam swap, you have to think of these other things as well. Things like your spring installed height, which is a result of your valve stem protrusion. You have to think of your spring seat pressure and your open pressures. Again, these are determined by the type of spring that you use. It's also determined by your valve stem protrusion, your valve lengths. And then you have to think about coil bind of the spring itself. You have to think about your guide clearance from the spring retainer on the inside and the clearance to the seal and the guide. And then, of course, the big one too, you have to think about valve to piston clearance. Every piston has valve reliefs in it, some larger, some smaller, and you have to be sure to match up the valve size you're running, make sure it's going to fit in that valve relief. So at this very specific point, when the piston's all the way up and both valves are off the seat, you're going to have proper valve to piston clearance as well. A lot of things to consider. Now let's go to a cylinder head, mock one up with the valves in it after the valve jobs have been done, and then we'll dial in these TDC lift specs and measure just how close the valves get. All right, so here we've got a twin cam cylinder head that we've already started machining. We've done the valve job on it. We've done, porting, obviously put the guides in it. So the first variable that we discussed is the valve size. So one of the things we've done on this head is increase the valve size over stock. So as you increase the valve size over stock, the valves do get closer together. So that's one thing we have to consider. Valves get closer together. All right. When we machine these valve seats, there's another very important dimension that we have to consider. And that other variable was valve stem protrusion, which is how far the valve is sticking out from the seat right here on the head. Now, a thing about Harley engines, it's not like a small block Chevy, for example, where you have a rocker arm stud in the middle with a ball on it, and then you have a push rod and a valve on the other side, and the rocker arm can kind of float between the two. On a Harley engine, you actually have this cam support plate here. The plate bolts in like this, and then your rocker arms are in a fixed, in a fixed position, right? They can't float. So if your valve stem protrusion is too tall or too short, you can actually side load the valve and create excessive wear on the valve stem here and also in the valve guide. So the valve stem protrusion number, and staying within that specification to maintain the angle of the rocker arm on it, keeping the tip centered on the stem of the valve, and trying to keep that valve as straight without side load, that is a very critical dimension. Now on M8 heads, it's even more important because you're actuating two valves with a single stationary rocker arm. So that valve stem protrusion from one valve to the next has to be absolutely spot on perfect. So what you're trying to do here, you have to, at the same time, you're sinking the valve further in the head, but when you do that, you are also getting a resulting valve stem protrusion. That's where the other variable comes in, which is the length of the valve stem itself. Sometimes you, even on custom engines, you'll have to grind the end of the valve stem here to shorten it up a little bit to get that proper protrusion. So that's the other variable. Now, the other thing you have to be careful of, again, with that TDC lift and the cam that you're running with this particular build, you have to sink the valve far enough into the head so that you have enough valve-to-valve clearance at the TDC lift. And I'm going to show you how we check that number. First off, you put your valve in the head, you put a lightweight spring on it with a retainer, and then you put this fixture on it. Now, this fixture has two dial indicators on it, and I choose to use half thousandths indicators to know that I'm exactly on the money. Now, I want to compare this to the 4 cam profiles and then show you guys how close the valves will actually be to each other at that TDC point. I think you're going to be very surprised. So let's start with the first camshaft, which is going to be the S&S 570 that has an intake TDC lift of 187 and an exhaust at 179. That's 50 thousandths, 100, 150, and we're going to dial this in. We're going to dial this in to 187. Now let's dial in to the exhaust side, which is 179 thousandths. There's 50, 1, 150, 160, 170, 5, 6, 7, 8, 9. Now you can see how close the valves are to each other. Let's slide a feeler gauge in there and see what that distance is. Now, I have a particular target number that I'm looking for. I like to have about 60 thousandths in here. Different builders will have different numbers, but I like to allow about 60 thousandths in there in case someone wanted to go to a bigger cam later. They would have a little bit more room, and in case there would possibly be a little bit of valve float or something like that. We know we've got enough room, and we know these valves are not going to hit each other if we have 60 thousandths of an inch. Remember, 60 thousandths is very small. This right here, in fact, is 60 thousandths of an inch. Very close to each other. And let's see if we have enough clearance. And in fact, we do. We have 60 thousandths of an inch clearance. So we would be okay to run an S&S 585 cam. We also know that we would be okay to run the S&S 570 cam because, again, those numbers were very, very close to each other, right? Now, let's dial in the Redshift 577 and see how much this changes. Now, the Redshift 577 has a 214 on the intake. 10, 14. And then we have 197 on the exhaust. So let's do it again. Perfect. Now let's see what our clearance is. We're definitely not at 60 thousandths anymore. Let's go to 30. 30 will fit. So let's try 40. 40 is a little snug in there. All right, so you can see with basically we're running virtually very similar middle of the road total lift cam, but yet our clearances here are quite a bit different, almost half the amount. Now, one thing to consider, there is a bit of dynamic compression in a valve train while the engine is running. How much exactly that is, there are some theoretical values and relatively close numbers, and basically what that means is while the engine is running, the lifter is going to collapse just a little bit, the push rod will shrink just a little bit, the rocker arm will flex a little bit, so in the end, you don't have quite as close of a fit here dynamically as you do statically. But we prefer not to take the chance. Now, let's look and see what happens if we put in a cam for the Redshift, let's say that the Redshift 627, which had a 240 and a 207. There's our 240. Now let's do the exhaust. Now I know we're going to be getting pretty close, so I'm going to flip the head over once I start and make sure that the valves don't hit each other along the way here. And we're going to go to a 207 on the exhaust. Okay, now a 207 on the exhaust. And let's look at how close these are together. I'm going to say we've got somewhere around maybe 20 thousandths in there at best. I believe we're right at 20. Let's step that up just a little bit. Let's say maybe 24, 25. There's our point right there. So we only have 25 thousandths clearance here. I'm going to give you a little closer look. How close those are together. The other variable I didn't mention when I was at the whiteboard is how your machinist has set up your heads. How far they choose to separate that valve to valve when they're setting their valve stem protrusions and sinking the valve. That number can change. We like to use a broader number, around 60 thousandths. Others will use tighter numbers and in order to squeeze a bigger cam in there, or maybe even squeeze bigger valves in there, and they'll run that number much, much tighter. But if you don't know what that valve to valve is, then choosing a cam could be absolutely destructive to your engine if you don't choose the right one. So in short, before you swap cams, talk to the person that did your cylinder heads, or when you get your cylinder heads done, make sure to ask your builder how big of a cam you could go in the future if you decided to change it up. And that's it. Guys, as always, thank you for watching. Take care of yourselves and each other. We'll see you on the next one. Have a good one.